Guys, welcome back to the second half of our lesson on the transformation of functions. We're going to pick up in your student workbook today on page 59 with horizontal dilations. This is example number 4. Now, in Algebra 1, I taught you that if the coefficient of the x term was a positive number, that it was going to be a happy face, and if it's a negative people are always frowning, so it gets flipped upside down. But it's important to notice that that is inside the parentheses and it's being squared. So what happens if I square a negative number? It becomes a positive. So no matter what, this is going to come out as a positive. So still it should be a happy face because positive people, hopefully, positive people are smiling, making a happy face. So let's look at this. This number here, the absolute value of it is greater than 1. So that tells me that I'm compressing that graph horizontally, which is kind of like stretching it vertically. It's making it grow this way. Let's look at the picture. We stretch it, stretch it, stretch it. We are multiplying by -1. We have the constant a is greater than 1 if we take the absolute value of it. So if we look at it like this, we have -1 times a times x, so that a is 2.5, which is greater than 1. So that tells me that it's being compressed horizontally and being reflected in the y-axis. So it's being reflected across the y-axis. So here is my graph that shows a compressed horizontal compression and a reflection across the y-axis. All right, let's talk about the transformations of functions. Again, this time we're looking more at the equation here and what happens. So the general form of the function, g of x, is some number a times x, your x value being evaluated, we're subtracting h units from it, and then on the outside of that, we're adding k number of units to it, where f of x, just plain old f of x, is the parent function. So each constant in the equation affects this parent graph. What this h here, whatever value it is, it's going to affect part of the parent graph. Whatever this value of k is, it's going to affect part of the parent graph. Whatever this value of a is, it's going to do something to the parent graph. Some of it's stretching, some of it's compressing, some of it's shifting up, some of it's shifting right or left. So it just depends on what that value is, and that's what we're going to look at here. So if a outside of the f of x is greater than 1, then that tells me that my graph is being stretched vertically. If it's in between 0 and 1, it's being compressed vertically, so it's getting wider. Okay? If a is greater than 0, that tells me that it opens upward. It's a happy face. Positive people are smiling. If a is less than 0, then it's a frowning face because we know negative people frown. And that frown upside down is when a is positive. All right, so let's look at this the other way. If the absolute value of a is greater than 1, then the graph is stretched vertically. If the absolute value of a falls between 0 and 1, then the graph is compressed vertically. So here's the stretch vertically greater than 1, and here it is being compressed vertically when it's between 0 and 1. I like that. Let's look at this one. Let's look at this one over here. A is less than 0. It gets reflected across that x-axis and it becomes a frowny face. All right, so let's talk about horizontal translations. When the h, that's this inside parentheses, is greater than 0, the graph is translated to the right. When h is less than 0, then my graph is translated to the left. So I've got my h is equal to 0 right there. H is a positive 2, we'll say it shifts 2 units over. H is negative 2, it shifts 2 units to the left. The tricky part is that if h is negative, in the equation up here, we have a minus. It's already a part of the equation, so minus a negative turns this into a plus. So we see that plus h and we think, oh, it's plus h, I should shift to the right. But we have to remember that the original equation is minus. So when I minus -2, I get a +2, so that's why it shifts to the left. If I minus a +2, I just have -2, so it shifts it to the right. So then I'm sure you can assume what this k does. That's my vertical translation up, or it goes down, however many units this is. So let's watch the little video here. If k is greater than 0, it goes up. And for values of k less than 0, that's negative numbers, it shifts downward. All right, so let's look at some problems over this. Doing multiple transformations of a function. So we've got multiple things happening here. We've got this -2/3 outside of the x plus 3. We've got this plus 3 inside of there. And I've got this plus 1. So I know this 2/3 is, being negative, is going to cause a reflection. I know the 2/3, it's less than 1. So that's going to cause it to be compressed vertically. I know that this plus 3, it should be x minus a -3. So that shifts it to the left 3. And this plus 1 is going to shift it up 1. So let's look at it. Boom. There's the reflection because it's negative. Okay, what else happened? Because a is less than 0 and the absolute value of a is between 0 and 1, that 2/3 is between 0 and 1, we know that it gets reflected across the x-axis and it is compressed vertically by a factor of 2/3. So we go down 2 over 1, 2, 3, down 2 over 1, 2, 3 to get our points. Okay. Then it's important to realize that we take that once we get the reflection and the new steepness of it, and we've got to shift it to the left 3 units. Remember, this is supposed to be minus in here. So in order for it to be a plus, it must have been minus -3. So that shifts it over 1, 2, 3. And then this plus 1 shifts it up 1. So we have our new function. This took a shift from the parent function. It flipped. It stretched, not really stretched, it compressed vertically, it got wider, and then it shifted over, and then it shifted up. And that's how we do that. Okay, applying another transformation of functions in example 6. I am on page, what page am I on? Example 6, I believe, is on page 61. All right. Dolphins. Bottlenose dolphins can jump as high as 20 feet out of the water in order to communicate nearby danger or prey. Suppose the path of a dolphin during a jump is modeled by this function, where x is the horizontal distance traveled by the dolphin and g of x is its height above the surface of water. Describe how g of x is related to its parent function and interpret the function in the context of the situation. So we're looking at this. I see some key things here. This negative outside of the squared, so I know it's going to be reflected. This value is in between 0 and 1, ignoring the negative. It's in between 0 and 1, so that tells me that it's getting compressed vertically. This minus 12, minus is part of the formula, so this is a positive 12. That is, so it's being shifted to the right 12 units, and then this positive 18 tells me it's being shifted up 18 units. So let's fill that in. So the graph of x squared is translated 12 units to the right. Okay, 18, that's the value of k. It's out here, so that tells me it's going up 18 units. Okay, the absolute value of negative 0.125 is in between 0 and 1, so that tells me it's being compressed vertically. Remember, if it's greater than 1, it gets stretched, but if it's less than 1, it's getting smashed down, getting compressed vertically. And since a is less than 0, it gets reflected across the y-axis. So because a is negative, the path of a dolphin is modeled by a parabola that opens downward. This means that the vertex of the parabola is HK, so our H is 12, our K is 18, and that represents the maximum height of that dolphin as it's jumping up. The vertex would be that highest point there on that parabola. So think about it, it's like this, that's going to be the highest point. That's why I said it's the maximum height. We can check our answers. Move by. Okay, moving on. Example 7. Identify an equation from a graph. So we've got this graph. I can tell that it is an absolute value function because it is a V shape. We can look at the steepness. It goes up 1 over 1, 2, 3. So I know there's a 1/3 in front of my x, right? 1/3 in front of the x because it has a slope of 1/3, and on this side a slope of negative 1/3, but it's inside the absolute value, so we go with the 1/3. Okay, it has a vertex here at -1, -2, -3, -1, -2, -3, -4. So -3, -4 is my vertex. So that's my H is -3. My K is -4. So all we have to do now is fill it in to our equation. So I need a piece of paper and a pencil here. I said -3, -4 was my vertex. So, and I said my slope was 1/3. So writing it out, I've got the absolute value of 1/3 x and minus a -3. Instead of writing minus a -3, we know that minus a negative is the same as plus 3. Then I close the absolute values. Then outside of that, I'm going to have -4. Let's go down here and check. We analyzed our graph. We identified the translation. Since the vertex shifted 3 units left, our value of H is -3. Shifted down, so our value of K is -4. We plug it in and evaluate. Minus the negative becomes a positive. Step 3 says to then plug in a 0. Let's see, what are they doing here? Use the equation from step 2 and a point on the graph to find the value of A. I already knew the value of A because I just looked at the steepness of the graph. But if you don't do it that way, you can, this is another way to go about doing it. Just pick out a point, 0, -3, plug it in and solve for A. That works too. Either way you go, you get the same thing. We get this 1/3. So it says, watch out. Choosing a point. When I'm substituting in for x and y in the equation, use a point other than the vertex. So what that's saying is you don't want to plug in this point because think about it, you've already used that point, -3, -4, so that's not going to be helpful. You need to pick out another point. So they used this 0, -3 point right here, which is essentially what I did. It's the same thing as what I did. I just didn't plug it in and solve algebraically. I looked at the picture and solved it that way, up 1 over 3. So either way you go, we get the same answer, and our equation is 1/3 times the absolute value of x plus 3 minus 4. And that takes care of it. And that is our final example for today. So hopefully you enjoyed this lesson. Hopefully more than enjoying it, you learned something. Hopefully you took some notes in your workbook. And I highly suggest practicing some of the odd problems and then checking your answers in the back of the book just to make sure that you truly understood it. It's easy to understand it when I'm teaching it and going over it, but then when you try it on your own is when you realize if you really understood the lesson or not.